Imagine a battery that not only withstands the rigors of everyday life, but also promises to run over 1,000,000 miles without breaking a sweat. Well, that's exactly what Tesla is bringing to the table with the new 4680 Gen 2, developed specifically for the Model 2. But don't think it's just any old update. What they've done here is almost like ripping up the previous manual and writing a new one from scratch. The battery structure has been redesigned to be lighter, more compact, and much more efficient, with a tableless architecture that immediately catches the eye. And you know that story about how it takes hours to charge an electric car? This one, in tests, can reach up to 80% in less than 10 minutes. This changes everything, and not just for drivers, but for the entire industry. Now, let's talk about the internal chemistry of this beast. Tesla replaced the traditional nickel-cobalt cathode with a lithium iron phosphate (LFP) blend, which is safer and cheaper to produce. And the coolest thing is that even though it's cheaper, it doesn't lose power because it was combined with a doped silicon anode, which increases energy density. It's as if they got the best of both worlds: the durability of LFP with the performance of silicon. This combination also helps keep the battery stable in extreme temperatures, which is a huge improvement for those who live in very hot or cold regions. Furthermore, this new chemistry allows the car to charge quickly without frying the battery inside. Another point that can't be overlooked is the Gen 2's self-repair system. It sounds like something out of science fiction, but the battery literally regenerates over time. It uses a flexible gel electrolyte that settles inside the cells and redistributes lithium ions when the car is parked. This prevents those internal microcracks that often kill a battery over the years. In tests, this system has shown that it can maintain up to 90% capacity even after more than 10,000 complete charge and discharge cycles. Now think, that's the equivalent of driving over 1,000,000 miles with the same battery. It's the kind of thing that makes you rethink whether it's really worth replacing your car every 3 or 4 years. The size has also changed. Gen 1 was 80 millimeters tall, but Gen 2 is 30% more compact, at 70 millimeters, which may seem small, but in the world of electric cars, every millimeter counts. This reduction in volume makes it easier to install in smaller models, like the Model 2 itself, and also improves weight distribution in the chassis. This means the car is more stable in corners, safer in collisions, and with firmer handling. Most impressively, even by reducing the size, they manage to maintain, and in some cases even increase, energy density, thanks to internal improvements in the composition and layout of the cells. To top it all off, there's the cost factor. Gen 1 was still expensive to produce, even though it was manufactured in-house by Tesla. Gen 2, however, has been optimized to make everything cheaper. The cost per kilowatt-hour could drop to less than $60, which, in practice, puts the Model 2 very close to the target of selling for less than $15,000. This cost reduction, combined with the increased lifespan and charging speed, makes it clear that this battery wasn't just made to shine in the lab. It was designed to run on the street, handle traffic, hit the highway, charge quickly, and last for years, all with minimal maintenance. And it's precisely for these reasons that Gen 2 is attracting so much attention. Because, at its core, it's not just a new battery, it's a reinvention of how an electric car should be built. While the world is still digesting the arrival of the 4680 Gen 2, Tesla is already testing a game-changing ace up its sleeve: the NCO5 battery. It doesn't follow the company's trademark cylindrical shape. Instead, it adopts a prismatic shape, more similar to what you see in some Chinese batteries, but with one glaring difference: it delivers Pantun Weichkeek Goff energy density. This places the NC05 at a level few batteries in the world can reach. And the most curious thing is that, despite this incredible advancement, it doesn't rely on the typical materials that have created a certain dependence on the Asian market. It's as if Tesla is saying, "We're not going to play this game by other people's rules anymore." The secret behind NCOI5 is in the cauldron electrode technology, a process that eliminates toxic solvents and drastically reduces energy consumption in manufacturing. In numbers, this represents a savings of up to 40% in the cost per cell, which in itself would be a scandal in the industry. But the craziest thing is that these savings come along with a leap in performance. The dry electrode allows for thicker layers of active material to be created without compromising conductivity. This means more energy per cell, less heat buildup during use, and, best of all, less risk of internal short circuits. One of the nightmares of any EV manufacturer. Another notable feature is the recharge speed. Thanks to an optimized internal design, which combines the learnings from the 4680 with specific improvements, the NCO5 can recharge from 0 to 80% in less than 10 minutes. And this without requiring complex cooling systems. The battery was designed to operate with a simpler thermal system, using heat sinks and thermal pads instead of traditional liquid circuits. This not only reduces the weight of the assembly, but also simplifies maintenance and increases system reliability. All of this makes the NCER5 a perfect candidate for the Model 2, which needs to be inexpensive, durable, and simple to mass produce. And here comes the part that really shakes up the market. NC05 was created with complete independence from the Chinese supply chain in mind. Tesla has struck deals with US companies to extract, refine, and process the necessary materials, including lithium, nickel, and even silicon. This aligns production with Inflation Reduction Act criteria, guaranteeing tax incentives and positioning Tesla as the only manufacturer with complete vertical control over its battery production in the United States. While other automakers still rely on CATL licenses or contracts with Asian suppliers, Tesla is stacking megafactories within its own territory. It's a masterstroke that goes far beyond engineering. It's pure geopolitical strategy. But perhaps the most impressive statistic about this new battery is its cycle life. In tests conducted at Tesla facilities in Nevada and Texas, the NCO5 surpassed the 2 million miles of durability. That's 4 times longer than traditional batteries can last before they begin to lose performance. With this level of longevity, a single pack can last for decades, or be reused across multiple generations of vehicles. This places the Model 2 in a completely new category, where the car ceases to be just a means of transportation and becomes a long-term investment. If this battery does indeed enter mass production by 2026, as rumors suggest, Tesla won't just lead the EV market, it will rewrite it from the ground up. With a revolutionary battery at the heart of the project and a fully controlled production chain, the Tesla Model 2 is on its way to becoming the most affordable and durable electric car in history. What immediately catches your eye is the estimated price. As $10.7999 in an industry where the cheapest electric vehicles still hover around $25,000, this price tag seems almost a trick. But the explanation lies in the set of technical decisions that transformed the Model 2 into a kind of 21st century people's car. Starting with the simplified structure, which abandons traditional chassis components and integrates the battery directly into the car's platform, reducing weight, parts, and complexity. This model uses the concept of structural battery, where the power pack itself functions as part of the vehicle's structure. This means there's no need for extra supports, crossbeams, or additional reinforcement elements, which alone represents a savings of thousands of dollars per unit. Furthermore, the use of Giga Casting, a technique that molds large parts of the car from a single piece of cast aluminum, reduces assembly time and labor costs. It's as if Tesla looked at each manufacturing step and thought, how can we make this simpler, faster, and cheaper without sacrificing performance? Autonomy, by the way, was not sacrificed in this process. The Model 2 promises to reach between 250 and 310 miles per charge, which is more than enough to cover 95% of the daily needs of drivers in the United States. This range is made possible not only by the efficiency of the new batteries, but also by the vehicle's reduced weight and the use of optimized motors, likely with a single rear-wheel drive system. The decision to maintain a single motor, instead of an all-wheel drive system, also helps cut costs, simplify the drivetrain, and reduce overall energy consumption. All of this means the car not only costs less, but also consumes less energy per mile. And if you think that the Model 2's performance is lacking because it's cheap, it might be time to reconsider. The estimated 0-60 mph acceleration time is around 6.7 seconds. This puts the car ahead of many combustion engine sedans in the same price range, offering respectable performance for both urban and highway use. Top speed hasn't been officially announced yet, but considering the focus on cost-effectiveness, it should be more than sufficient for US and European roads. The most important thing here isn't to build a race car, it's a car that runs well, is reliable, and is affordable for those who've never considered driving a Tesla. Ultimately, everything about the Model 2 revolves around a very clear logic: delivering accessibility without sacrificing innovation. And this is only possible thanks to interconnected decisions across design, battery, motor, and manufacturing. By combining technologies like the 4680 Gen 2, the NC05, and Giga Casting into a single project, Tesla builds a vehicle that can be mass-produced, sold at a competitive price, and still maintain a healthy profit margin. The impact of this goes far beyond Tesla itself. This model has the potential to redefine what the market considers an entry-level car, and force the entire industry to pursue similar solutions. And, by all indications, the next move involves cutting the last major external dependency: the materials that make up these batteries. With the goal of making the Model 2 truly independent in every sense, Tesla decided to attack the root of the supply chain: materials. The company has been investing heavily in creating a production infrastructure 100% located in the United States, betting on American suppliers like Piedmont Lithium, Albemarle, and Silla Nanotechnologies. This isn't just a matter of logistics. It's a strategic move that puts Tesla at the forefront of a global movement toward industrial autonomy. After all, no matter how advanced a battery is, if it relies on Chinese graphite, Congolese cobalt, and Russian nickel, it remains vulnerable to geopolitical crises and market fluctuations. What Elon Musk and his team understood is that the future of electric cars depends not only on technological innovation, but also on supply chain security. And when the US passed the Inflation Reduction Act, offering up to $7,500 in incentives per car with locally sourced parts and materials, Tesla wasted no time. It restructured contracts, accelerated construction of new factories, and began developing technologies that replace critical components with more abundant and cheaper alternatives, all within US borders. This stance puts companies like Ford, GM, VW, and Hyundai in a difficult position, as many still rely on batteries, cells, and technology licensed from Chinese suppliers like KATL and BYD. Another key point of this turnaround is in the graphite, one of the main inputs for lithium-ion battery anodes. Today, over 90% of processed graphite comes from China, which represents a huge bottleneck. Tesla, however, has invested in high-performance silicon anodes developed by American startups, such as the aforementioned Silla, which promises to not only eliminate the use of graphite, but also increase energy density by up to 20%. And by replacing the traditional nickel-cobalt cathode with alternatives such as LFP or alloys with low noble metal content, the company can cut costs and reduce its environmental impact, in addition to eliminating its dependence on materials whose mines are under constant ethical scrutiny. With all this, Tesla gains more than logistical control. It gains industrial resilience. While competitors still negotiate with mining and shipping companies on the other side of the world, Tesla concentrates production, refining, assembly, and distribution in a few US states. This means fewer bottlenecks, fewer delays, and more control over quality and pricing. And with the Model 2 poised to become the company's highest volume product, this verticalization of the supply chain is essential to scale production without relying on anyone. It's the kind of move that, from the outside, may seem subtle, but from the inside, it completely changes the pace and structure of automotive production. And it's not just about manufacturing faster or cheaper. It's about paving the way for a new type of electric mobility, where the car not only consumes energy, but also actively participates in the grid. With durable, domestically produced, safe, and recyclable batteries, the Model 2 fits perfectly into the idea of a sustainable energy ecosystem, connecting with solar panels, residential storage, and even the public grid. And that's exactly where the next piece of this puzzle comes in. A technology that can make batteries even cheaper and more efficient. A battery made from something surprisingly common: aluminum. When it comes to aluminum batteries, many people turn up their noses thinking it's just laboratory talk. One of those ideas that only works in prototypes and never leaves the test bench. But Tesla seems poised to change that perception. The so-called aluminum-ion battery has entered the testing phase, and if the numbers hold true, it could simply obliterate everything we know today about cost and autonomy. To begin with, the estimated cost per pack is only $1,350. That's right, less than many top-of-the-line cell phones on the market. Such a price, for a component that was previously the most expensive in the entire car, completely changes the game for affordability in electric vehicles. Aluminum has always been an abundant, inexpensive, and easy-to-recycle material. But until recently, it wasn't viable in batteries due to the difficulty in controlling the charging and discharging processes with stability. Now, with new electrolyte technologies and molecular engineering, this problem appears to be solved. Tesla is reportedly using a proprietary gelatinous electrolyte formula that prevents the formation of dendrites, structures that, in other batteries, cause short circuits and loss of efficiency. This new type of electrolyte, besides being safe, allows for much faster ion flows, which paves the way for extremely short recharge times, even without the use of rare earth metals or expensive cooling systems. And here comes the most surprising detail. The estimated autonomy with this new type of battery is up to 550 miles per charge. That's more than 880 km a single charge. We're talking about a range superior to that of many combustion engine cars at a much lower cost. This battery could make the Model 2 not only Tesla's cheapest car, but also its most durable and long-lasting. If the promise of performance combined with longevity comes to fruition, a Model 2 with an aluminum battery could run for decades without needing replacement, especially with the self-healing structure already being tested in the company's other lines. The most interesting part is that aluminum allows for creative solutions that other chemistries can't tolerate. Because it's less sensitive to thermal variations, cooling systems can be drastically reduced, meaning less weight and fewer points of failure. Furthermore, aluminum ion has a more linear discharge behavior, which helps battery management software more accurately predict remaining range. Something that, let's face it, still causes anxiety among many EV drivers. What's more, because it's a widely used material in industry, aluminum is compatible with large-scale manufacturing processes, accelerating the technology's transition from the laboratory to the production line. Ultimately, what Tesla appears to be doing with this battery is more than just innovating. It's redefining what it means to build an electric car. By combining ultra-low cost, massive range, and extreme durability, the Model 2 with an aluminum-ion battery could become a game-changer not only for Tesla's lineup, but for the entire automotive industry. And now, for the first time, the future doesn't just look electric, it finally looks viable for anyone. It's the kind of breakthrough that not only changes the product, but changes the consumer, changes the mindset, and forces the rest of the market to urgently catch up. Because the truth is, If Tesla really puts this car on the streets for less than $11,000 with a battery that lasts millions of miles, then yes, we're looking at a revolution.